Dr. Jerome McClendon is an accomplished researcher and research assistant professor in the Department of Automotive Engineering at Clemson University. He is a recognized expert in human-machine interfaces, or in short, HMI, and has contributed extensively to the development of advanced autonomous vehicle technologies. Dr. McClendon's research focuses on the design of intuitive and user-friendly interfaces that enable seamless communication and interaction between humans and autonomous systems. His work has been recognized with numerous awards and honors. At the Automotive AI Summit, Dr. McClendon shared his expertise on the topic of future human-machine interfaces for autonomous vehicles. Future human-machine interfaces for autonomous vehicles is an important topic because it addresses one of the critical challenges in the development and adoption of autonomous vehicle technologies, that is, the need for intuitive and user-friendly interfaces that enable seamless communication and interaction between humans and machines. As autonomous vehicles become more prevalent, the ability of humans to interact with these systems in a safe and effective manner becomes increasingly important. Human-machine interfaces plays a critical role in ensuring that the human driver or passenger can understand and control the autonomous system's actions. The development of intuitive and effective HMI for autonomous vehicles has the potential to improve safety, increase user acceptance, and accelerate the adoption of these technologies. Therefore, understanding the latest development in HMI design and their potential impact on the future autonomous vehicles is an essential for anyone interested in the development of advanced transportation technologies and their potential impact on society. So let's welcome Dr. McClendon.
Good morning, everyone. So my name is Jerome McClendon. I'm a research assistant professor here in automotive engineering, and I was also the software integration lead for Deep Orange 10. And today I'll be talking about the future of HMI for autonomous vehicles, with the use case being Deep Orange 10. So in Deep Orange 10, we were challenged by Ford. It was a project in collaboration with Ford to design the future autonomous vehicle for the year 2030. And the students came up with this unique idea of autonomous rideshare. And this idea is like, if you go to work or you go home, can I actually Uber out my vehicle while I'm at work and at home and make money on the side? So that was the idea that they came up with for the use case, and Ford challenged them to make a fully automated vehicle. They were actually successful in the development of this fully automated vehicle. But Ford also challenged them to think about, how can we come up with a human-machine interface that could support fully automation? So they came up with this architecture that you see above, with the human-machine interface being in the center and controlling stuff such as the vehicle control, authentication, external communication, and the user experience. But if you look inside the actual Deep Orange 10 vehicle, you'll notice that there's no methods there's no steering wheel, there's no pedals. So that created a challenge in how does the human actually override the vehicle from a user perspective. So and specifically, focuses on how do we actually communicate intentions? So if I wanted the vehicle to park in a certain spot, or if I wanted to change direction, since I don't actually have the steering wheel, how do I actually communicate that information? And this was actually done through our HMI system, or our human-machine interface system. So one example of where we use AI in our human-machine interface was actually in the speech recognition system. So let me play the video. Okay, so the video is not going to play actually the video sound, but in this actual video, you'll see, or you will hear the system actually say, where do you want to navigate to? And the person actually responded 356 restaurant. So this required us to use a speech recognition library. The students did not create their own speech recognition library because we only have 2 years, but they were able to use the Google speech recognition library, and it successfully worked. But one of the challenges that we realized, and this is a challenge with any kind of machine learning system, especially with speech recognition, is having data actually customized to that user. So a lot of our students actually came from India. So we had challenges around dialects in this specific use case. Then another thing that the students used artificial intelligence in was the actual gesture recognition. So being able to not only speak to the system, but being able to actually point and give gesture commands. So in this example, you'll see the student actually controlling like the phone system within the actual vehicle and doing gesture recognition. So we did develop this from scratch, and we used a 3D camera, and we created the algorithms to actually do the gesture recognition detection. So this is basically how we communicate directly to the vehicle through the interiors. But we also had another challenge of how do you passively communicate? So if you look at this example, and this is a good example from the video perspective, in that in an autonomous vehicle, the first thing people may do since they're no longer driving is read. If you ever been on like a bus system and you get on the bus and you start reading, the first thing you might start feeling is motion sick. So one of our challenges with Deep Orange 10 was how do we create an artificial intelligence system or algorithm to actually detect motion sickness? And so the students came up with this algorithm that you see actually on the screen. So we got a wearable, a hand wearable or a wearable on the wrist, and we were able to get like accelerometer data, heart rate data, electrodermal activity, and the wrist temperature. We were able to take those signals and fuse it into what we call a growing neural gas algorithm. So a lot of people are familiar with deep learning and deep learning systems, but one of the challenges with deep learning is that you require a whole lot of data. Given that it was only a 2-year span, we couldn't collect that data from a wide variety of people. So we used an unsupervised approach, or what they would call a self-organized neural network. And so we were able to take that information, and then it was supposed to control the actual, maybe the drive parameters or change the lighting to actually control motion sickness. Another challenge that we realized from the HMI perspective is now that you have these autonomous systems, how do they actually communicate trust? Like a lot of people don't trust autonomous systems. And how do you actually communicate that trust? So we came up with an external HMI, which we call the external communication system. And basically, this allowed people on the outside, pedestrians, to know what were the actions that the AI system or the autonomous system would take. And right here is an example of where the actual screen would light up and say passengers boarding. Another example would be that the vehicle, when the vehicle came to a stop, it would say vehicle stopping or something like that, or vehicle slowing down. And the last challenge, and I mean, this was a challenge that me and Pisu, who also was the project lead for Deep Orange 10, was in order to improve these algorithms, the speech recognition algorithm, the gesture recognition algorithm, to improve even the self-organizing algorithm to detect motion sickness, we had to actually collect data. So to get these algorithms up to a certain accuracy, we needed more data. But the challenge with this, and I think this is a challenge that a lot of people overlook, is how do you actually collect that data and how do you actually keep it private? Am I willing to actually share my speech, my voice, my gestures, or even my physiological activity to a cloud system? So we followed up Deep Orange 10 with a grant to the Department of Defense looking at privacy-preserving machine learning algorithms. Where we first started off with focusing on federated learning, we later moved to homomorphic encryption. And both of these things are a large challenge for the research community because it is not only related to accuracy, it's a balance between accuracy and the computational expense, which includes having the computational power and the speed to actually perform these actions. And that's it. Questions? So the actuation side, we didn't have, so that actually didn't, in the end, we could detect motion sickness, but we didn't implement that into the actual controller where it would actually change its drive parameters and all that. Yep, that was the plan. Thank you.